Hello students, welcome back to JJ's physics class. Today we are going to solve numericals based on ray optics and optical instruments. In order to solve numericals on physics, first of all you need to memorize all the formulas. Then second part is your concept of theory part should be clear. So let us start solving. Question number 1. You are given three lenses L1, L2 and L3, each of focal length 20 cm. An object is kept at 40 cm in front of L1 as shown. The final real image is formed at the focus of L3. Find the separation between L1, L2 and L3. So what is given here? Given for lens L1, object distance is given, focal length is given. So F1 is 20 cm, U1 is minus 40, minus value because the distance measured to the left side of the lens is taken as negative. Then using the formula, you can calculate the image distance of L1. So you get it as 40 centimeter. Next for lens L3, we know the focal length F3 is 20 centimeter and V3 is 20 centimeter. So using the formula, you can calculate the object distance of L3, which gives you what? Infinity. So image by L3 is formed at the focus so that object should lie at infinity for L3. So L2 will form image at infinity and object for L2. So the distance between L1 and L2 will be what? V1 plus F2. So 40 plus 20 will give 60 centimeter. But we have seen that the image by L1 is formed at 40 centimeter right of L1, which is 20 centimeter left of L2. So that means the distance between L2 and L3 can have any value. Question number 2. You are given three lenses L1, L2 and L3, each of focal length 15 centimeter. An object is kept 20 centimeter in front of L as shown in figure. The final real image is formed at the focus of L3. Find the separation between L1, L2 and L3. As you can see here, same as the previous question. So we have to calculate the image distance of L1 using focal length and the object distance. Here again the object distance is taken as negative. So V1 we will get it as 60 centimeter. So the image distance of lens 1 will be 60 centimeter. Next, using lens L3, so we can calculate the object distance of L3, that is equal to infinity. So now for lens L1, the image is formed at a distance of 15 centimeter from L2. So the object distance for L2 will be 15 centimeter. Now the distance between L1 and L2 will be what? V1 plus U2. 60 plus 15 will give you 75 centimeter. So distance between L2 and L3, that is V2 plus V3, can be infinity or it can have any value. Next question. A biconvex lens made of transparent material of refractive index 1.25 is immersed in water of refractive index 1.33. Will the lens behave as a converging or diverging lens? Give reasons. So here the answer is, use the formula 1 by F is equal to mu minus 1 by R1 minus 1 by R2. So using that, if you take the ratio of refractive index of two values, we get it as 0.98. Just because the refractive index of water is more than that of the material of the lens. So the F value will be negative, that is focal length is negative and it will act as a diverging lens. Question number 4. A convex lens is placed in contact with a plane mirror. A point object at a distance of 20 cm on the axis of this combination has its image coinciding with itself. What is the focal length of the lens? As you can see here, convex lens is in contact with a plane mirror. So, what is the focal length? Can anyone say? Focal length will be about 20 centimeter. What happens here? The rays coming out from this lens will incident normally on the plane mirror. What happens? It will reflect or retraces the same path as that of the incident ray. So the final image will be overlapping with what? The object. So the focal length will be about 20 centimeter. Next question number 5. When red light passing through a convex lens is replaced by light of blue color, how will the focal length of the lens change? Here the focal length of lens will decreases because refractive index of blue light is greater than that of refractive index of red. Next question. If the wavelength of light incident on a convex lens is increased, how will its focal length change? Focal length and wavelength are directly related. If the wavelength of incident light of a convex lens is increased, the focal length also increases. Next question. Two thin lenses of power minus 2D and 2D are placed in contact coaxially. What is the focal length of the combination? What is the formula here? We know that power is equal to 1 by F or F is equal to 1 by P. So power of combination minus 2D plus 2D will give you what? 0. Then focal length 1 by power 1 by 0 is equal to infinity. So focal length of the combination is what? Infinite. Next question. Two thin lenses of power minus 4D and 2D are placed in contact coaxially. Find the focal length of the combination. So power of combination here is what? When you add these two, you get it as minus 2D. Then total power is what? We get it as minus 2D. Then focal length 1 by P is equal to minus 1 by 2, which is equal to 0.5 meter. So minus 50 centimeter is the answer. So focal length is equal to minus 50 centimeter. Next question. How would a biconvex lens appear when placed in a trough of liquid having same refractive index as that of the lens? Here the answer is the lens will disappear or invisible and there will no converging or diverging action of the lens. Next question. Two thin lenses of power plus 6D and minus 2D are in contact. What is the focal length of the combination? So we have power is plus 4D. So focal length is 1 by power. So if you calculate the focal length, what we get is equal to 25 centimeter. It is a positive value. Next question. You are given following three lenses. Which two lenses will you use as an eyepiece and as an objective to construct an astronomical telescope? So L1, L2, L3 is given. Power and aperture is given. Objective, less power and more aperture. So L1. The one facing the distant object is called the objective and has a large aperture and large focal length. The other is called the eyepiece. So the eyepiece is placed close to it. It has a small aperture and a small focal length. So the objective is less power and more aperture. So lens L1 is used. Eyepiece lens L3 is used. Next question. A converging lens of refractive index 1.5 is kept in a liquid medium having same refractive index. What would be the focal length of the lens in this medium? So we have the lens maker's formula. Calculating that, you will get it as F is equal to infinity. Because when you substitute the values, mu1 and mu2 will be what? It is same. It's clearly mentioned it is same. So mu1 is equal to mu2. So 1 by F will get it as 0 or F value will be infinity. So the lens will act as a plane sheet of glass. And we know that the focal length of a plane sheet of glass is infinite. So the focal length of the given lens in this new medium would be infinite. Next, a biconvex lens made of transparent material of refractive index 1.5 is immersed in water of refractive index 1.33. Will the lens behave as a converging or diverging lens Give reasons. So the lens will behave as a converging lens because when you take the ratio of refractive index, you get it as 1.12, which is greater than 1. Hence, the value of f will be positive. Since the focal length is positive, the lens will act as a converging lens. Next question. When an object is placed between f and 2f of a concave mirror, would the image formed be real or virtual? And second case, diminished or magnified. So what happens when an object is placed between f and 2f of a concave mirror? So as you can see here, this is the diagram here. So the image is formed here. First case, it is real and it is also magnified. So that is the answer. Next, when light travels from a rarer medium to denser medium, the speed of light decreases. Does the reduction in speed imply a reduction in the energy? The answer is the reduction in speed due to light traveling from a rarer to denser medium does not imply reduction in energy because the frequency of light remains unchanged and the energy of a light photon depends only on its frequency. Next question. A biconvex lens has a focal length 2 by 3 times the radius of curvature of either surface. Calculate the refractive index of the lens material. So we have the lens maker's formula and substitute the values. So F is what? 2 by 3 times R. So R1 is equal to plus R, R2 is equal to minus R because it is a biconvex lens. Substituting all the values, you get the refractive index values are 1.75. Next, find the radius of curvature of convex surface of a planar convex lens whose focal length is 0.3 meter and the refractive index of the material of the lens is 1.5. So you need to calculate the radius of curvature. So F is given 0.3 meter which is equal to 30 centimeter. R1 is equal to infinity because for a plane surface, the radius of curvature would be infinite. And R2 we have to calculate. N value is given. So again use the lens maker's formula. So what do you get? R2 is equal to minus 15 centimeter. Question number 18. Out of blue and red light, which is deviated more by a prism? Give reasons. Next sub-question is, give the formula that can be used to determine refractive index of material of a prism in minimum deviation condition. So as you know that between blue and red light, blue light is deviated more by a prism. This is because the wavelength of the blue light is smaller than that of the red light. Therefore, the speed of blue light is lower than that of speed of red light. Or refractive index of blue light is greater than that of refractive index of red light. So blue light is deviated more by a prism than red. And the formula for calculating the refractive index of a material of a prism is N is equal to sine A plus delta M divided by 2 divided by sine of A by 2, where A is the angle of the prism and delta M is the angle of minimum deviation. So you have to be careful here because if it is a 2-mark questions, if you just write the formula, you get only 1 mark. But you have to also specify what is A is indicating, that is the angle of prism, and delta M is the angle of minimum deviation. So you must write this, where A is angle of prism and delta M is angle of minimum deviation. Next question. A ray of light incident on an equilateral glass prism, that is mu g is equal to root 3, moves parallel to the baseline of the prism inside it. Find the angle of incidence for this ray. So what is given here? Mu g is given root 3, that is refractive index of medium 2 with respect to 1. So we have the Snell's law, sin I by sin r, or root 3 is equal to sin I by sin r is given what? According to the diagram, it is 30 because it is an equilateral glass prism. So calculate I value using the logarithms. You get it as angle of incidence. I value will be 60 degrees. Thank you, students.